This is a short video on the product topology for two topological spaces. So the product topology on something like, I'll say x, say tx, and y, maybe I should say it this way. Product topology on x times y, where x and y are each topological spaces. So like product space is given two topological spaces, we can make a bigger space called the product space of x and y. And so how do we get the topology on this larger space? You can probably guess that it depends on the topology on x and the topology on y. And so maybe what is it? I'll say it this way. So this would be product topology on x across y. The easiest way to talk about it would be to tell you about it via a basis. So to tell you about a basis for the product topology. So what we're going to do is we're going to say that B1 say is a basis for topology T on X. Let's say that B2 is a basis for the topology, say fancy U on Y. Then a basis for product topology on X cross Y, so on the product space, is the following set. So it's going to be something cross something, and what we'll do is we'll take, say, regular U cross V, where regular U in the first slot, kind of like the product notation suggests, the first slot must be a subset of X, because X is in the first slot. And similarly, how should I say this then? So U is a basis element from X's topology T, and V in the second slot here, I'm just saying that that's a basis element of the topology on Y. So second slot stuff happens in Y. So V is in B2. So this is a great way to think about the product topology and say how you get it. And so let me give you an example. Now, of course, I'm giving you this in generality right now. Let me give you a specific example, though, of, say, product topology. So, for example, let's say R, real numbers, with, usual Euclidean topology. So what do we know? We know sets that look like A comma B with parentheses on both sides. This is a basis. So A less than B is a basis for that topology, for the Euclidean topology. So if I was to draw you a picture, hey, here's A comma B, and say that's like a regular open set in there, that's a basis element. And so what we're going to do now is we're going to look at R cross R now. So R cross R, that's the same thing as R2, and that's just the plane. So I'll draw that over here. So how do I talk about open sets in the product topology? What are going to be the open sets that are in the plane? And what they'll be is we're just going to have maybe a basis for product topology is, well, if I use kind of the idea up here, I should just find a basis for, each space in my product. In this case, it's both R, so I'll just use my regular open sets to look like this for both. So how do I get a basis for the product topology? I should just take basis elements from each space across each other. So in my example down here, I would take something like my picture, maybe I've got A to B is right here, and maybe I've got somebody like C to D is right here. Then an open set in R2 would be the little rectangle that I get by looking at, again, X values come from this interval, Y values come from this interval. So this would be open in the product topology. And so what is this? This is the set. These are what all like the basis elements look like. So the basis for the product topology is all sets of the form A comma B cross C comma D. Cross C comma D. So again, what that notation is supposed to suggest to you, if I could get the colors to line up, that would make me happy there. Great, cool. where, maybe I should say this too, A is less than B, C is less than D. The point though, these are where your x values come from, the green, and these are where your y values come from, the red. So that's an example of what the product topology is doing in that case. So again, Euclidean case is like the intuition. You should try to think about all this stuff through. But these definitions and stuff hold for, maybe much goofier topological spaces. Or maybe you've got like the lower limit topology. There's a homework problem about that. What else do we have? Other fun facts about the product topology. That allows us to, now that we've got an idea of a topology on the product space, we can talk about what it means to be, continuous. And there's also some special functions that we get on the product topology. So if I've got something where, let's say this is x and this is y, so I'm going to kind of draw my spaces. I've got two spaces, x and y. I'm going to draw them in 2 dimensions, but like maybe x is something weird and maybe y is something weird too. So don't put too much stock in this 2-dimensional picture. But I'm just trying to visualize. I've actually got a function that takes me from here. Maybe it just spits out this copy of x. And what we'll call that is we'll call that a projection. Maybe I'll call this, if this is x cross y, I'll call this, and our book calls this pi 1. So pi 1 is this function called the projection. It's the projection onto the first component. Onto first component. So what do I mean by that? So pi 1 is a function from x cross y to x, so onto the first component. And so how's pi 1 defined? Pi 1 of the point x comma y should be equal to, just tell me what x was, just tell me what the first component was. So in that case then, if you had a point like this in x times y, you would just figure out what this coordinate is, and it should just be set over here to x. I guess it would help me too if I labeled this. So pi 1 projects on the first component, and I've got another picture for a function called pi 2. So here's x times y. I'm going to tell you about this other function named pi 2 now. And so, well, let's say that I just project onto that y space there. So what am I trying to say? Here's this point here. I would just figure out what coordinate that is, and that's where it should go. That's the output of pi 2. So if I was to write this in kind of function notation language, pi 2 goes from x times y, but now onto the second coordinate. So again, projection onto the second component. When I say component, I mean, again, second component of the product. That's y in this case. And so there's some fun facts about pi 1 and pi 2. In particular, pi 1 and pi 2 are both continuous. Pi 2 both always continuous. No matter how weird your space x is, no matter how weird your spaces x and y are, pi 1 and pi 2 are always guaranteed to be continuous.